Welcome to the limit comparison test. So we had a limit comparison test for improper integrals. So recall that for improper integrals, if 0 is less than or equal to f of x and 0 is less than or equal to g of x, and if f and g have similar end behavior. So in other words, if the limit as x goes to infinity of f of x over g of x, it equals L, so it exists, then either both the integral from 1 to infinity of f of x dx and the integral from 1 to infinity of g of x dx converge, or both diverge. Technically, I should have mentioned that f and g are continuous and have similar end behavior. We got essentially that the convergence agreed between them. So they both converged or they both diverged as long as they had similar end behavior. So we get a comparable test for series. So the limit comparison test. I apologize for the noise in the background. So the limit comparison test for convergence for series states that if a sub n is greater than 0 and b sub n greater than 0, and if the limit as n goes to infinity of a sub n over b sub n exists and is positive, then this series either both converge or both diverge. So the series from n equals 1 to infinity of a sub n and the series from n equals 1 to infinity of b sub n either both converge or both diverge. There are a couple other cases here. It turns out that if the limit from as n goes to infinity of a sub n over b sub n equals 0, then if the sum from n equals 1 to infinity of b sub n converges, so does the sum from n equals 1 to infinity of a sub n. And if the limit as n goes to infinity of a sub n over b sub n is infinite, then if the sum from n equals 1 to infinity of b sub n diverges, so does the sum from n equals 1 to infinity of b sub, or sorry, of a sub n. All right, so note we lose the equivalency in these last two options. So if our limit as n goes to infinity of a sub n over b sub n is equal to 0, if a sub n converges or diverges doesn't necessarily tell us anything about b sub n. Similarly, if that limit goes to infinity, whether the series in A converges or diverges doesn't necessarily tell us anything about B. So from here, let's go ahead and move into an example. So let's use the limit comparison test to determine whether the following series converges or diverges. The series we're looking at is the sum from n equals 1 to infinity of 1 over 4n plus square root n. So let's go ahead and compare to the sum from n equals 1 to infinity of 1 over n. So I'm sort of looking at the highest degree term. So this was the highest degree term in the denominator was n, and then the highest degree term in the numerator was just 1. So what we get from here then is if I take my 1 over 4n plus square root n to be my a sub n, I take my b sub n to be 1 over n, then we have that the limit as n goes to infinity of a sub n over b sub n would be 1 over 4n plus square root n all over 1 over n. Sorry, limit of. We should still have a limit in front there. And of course, that is the same thing as the limit as n goes to infinity of n over 4n plus the square root of n. If we just multiply by 1 over n up top and down below, this becomes the limit as n goes to infinity of 1 over 4 plus the square root of 1 over n. And then as n goes to infinity, this is just 1/4. So this exists and is positive. Then since the sum from n equals 1 to infinity of b sub n, or the sum from n equals 1 to infinity of 1 over n diverges, that's our harmonic series, so does the sum from n equals 1 to infinity of 1 over 4n plus square root of n. So note, this is a comparison where if we did 1 over 4n plus square root n is less than or equal to 1 over 4n, right? The fact that the series of 1 over 4n diverges would do us no good. So this limit comparison test allows us to get equivalency in both directions, no matter whether a sub n or b sub n is larger. All right, let's go ahead and do one more. Let's use the limit comparison test to determine whether the series from n equals, or it is the sum from n equals 1 to infinity of the the square root of n cubed over n cubed plus 2n minus 1 converges or diverges. So let's go ahead and compare this to the sum from n equals 1 to infinity of the square root of n cubed over n cubed. Again, I'm just taking the highest degree terms. So using those highest degree terms, we can go ahead and simplify this to the sum from n equals 1 to infinity of, that's n to the 3/2 over n cubed. This would just be 1 over the square root of n cubed. So we can take our a sub n to be that square root of n cubed over n cubed plus 2n minus 1. We can take our b sub n to be 1 over the square root of n cubed, otherwise known as 1 over n to the 3/2. Then we have that the limit as n goes to infinity of a sub n over b sub n is the same thing as the limit as n goes to infinity of the square root of n cubed over n cubed plus 2n minus 1 all over 1 over the square root of n cubed. This, of course, is the same thing as taking the limit as n goes to infinity of the square root of n cubed over n cubed plus 2n minus 1 times the square root of n cubed, which is, of course, the same as the limit as n goes to infinity of n cubed over n cubed plus 2n minus 1. These have matching degree. So we can just take the leading coefficients. So this limit just goes to 1 over 1, otherwise known as 1. Again, this is positive and existing. So we have equivalency. And since the sum from n equals 1 to infinity of b sub n is just the sum from n equals 1 to infinity of 1 over the square root of n cubed, which is equivalent to the sum from n equals 1 to infinity of 1 over n to the 3/2. This converges. Again, here we have a p series with p being greater than 1, so we have convergence. Then we also have that the sum from n equals 1 to infinity of a sub n, or the sum from n equals 1 to infinity of the square root of n cubed all over n cubed plus 2n minus 1 also converges. So I often like to use the limit comparison test because we only have to worry about similar end behavior. We don't have to worry about one function always staying above or below the other. And then we don't have to worry about trapping above to prove convergence and trapping below to prove divergence. As long as they have similar end behavior, we're fine. So these are this is the last of the tests for this week for proving convergence or divergence.